Hi everyone, my name is Yihan Lin. I'm gonna do the question 1 of homework 11, so let's begin. Okay. And tells that the stochastic process xt is a real WSS, and it has autocorrelation Rx tau and the power spectral density. And for the subproblem A, it tells to prove that the autocorrelation is real and even. So we know that it tells us that xt is real, so the its autocorrelation based on its definition equals to the expectation of xt plus tau times xt. Obviously, the xt plus tau and xt is both real, so this expectation is definitely real. And then we have to prove it is even, so we know that Rxx tau equals to this Rxx t plus tau t based on its definition, and it equals to the expectation of xt plus tau times xt. And we can just exchange the position of these two terms. It equals to the expectation of xt times xt plus tau, and it equals to Rxxt t plus tau, and it equals to the Rxx minus tau. So we know that Rxx tau equals to Rxx minus tau, and we know it is even. So that's the subproblem A. And for the subproblem B, it tells to prove that the its power spectral density is even and non-negative. So first we're gonna prove it is even. So basically on the definition, so its power spectral density equals to the integral from minus infinity to infinity autocorrelation times the minus g times w g minus g times omega times t's power of e d tau. And we can substitute this power of e to cosine omega t and sine omega t minus g. So the whole integral will be separated into two parts. First, there's a real part. It's integral from minus infinity to infinity autocorrelation times cosine omega t omega tau times d tau, and minus this g times the integral from minus infinity to infinity Rxx tau times sine omega tau d tau. And we actually know that this autocorrelation is an even function here. And we know that sine omega tau is actually an odd function based on the properties of sine function. So we know that the even function times an odd function is an odd function. So, and the integral of an odd function will be equal to 0. So this non-real part will be just 0. So it will be equal to just this real part of it. So it will be equal to the integral from minus infinity to infinity autocorrelation times cosine omega tau times d tau. And we can substitute this omega tau to minus omega tau because it is an even function, and it will equal to the integral of minus infinity to infinity autocorrelation times cosine minus omega tau d tau. And we know based on the definition it is power spectral density as xx minus omega. So we know that this sxx omega equals to this sxx minus omega, so we now know that it is even. And then we will try to prove it is non-negative. And we know that based on fundamental theorem corollary, we have this expectation of yt squared equal to 1 over 2 pi times the integral from minus infinity to infinity sxx omega times capital H omega squared d omega. And we know that its expectation of yt squared is actually must be larger or equal to 0 because we have squares larger or equal to 0, so the expectation of it will be larger or equal to 0. So we know that this integral of this power spectral density times capital H omega squared, this integral will be larger or equal to 0. We can use an example here, like suppose that h omega equals to 1 when omega is larger than omega 1, smaller than omega 2, and it will be equal to 0 otherwise. It's an ideal bandpass system. And then we can know that this integral will be equal to this integral from omega 1 to omega 2 at power spectral density times d omega is larger or equal to 0 for any omega 1 and omega 2, because here we can set omega 1 and omega 2 to any value. And we know that this integral must be true for any omega 1 and omega 2, and if that's the case, then we must have this power spectral density as xx omega larger or equal to 0 for any omega. Otherwise, it won't be true for any omega 1, omega 2. So then we know that this power spectral density as xx omega is non-negative. So that's all for the question 1. So thank you.